Hi everybody. So today I'll talk about the 4 0 days I found in OpenVPN. Let's dig in. So this is Erlinda. She'll help me with the presentation. And our story begins one Saturday night, when I played Deep Rock Galactic with two of my friends, Nick and Philip. And so Philip had some lags, and the game wasn't working good for him. And so I asked him what's going on, and he said that he installed ExpressVPN. And so I started inquiring why he installed that, and he said privacy reasons, security reasons, all this kind of stuff. And so from there, I kind of tried to understand why he need that. And so he told me that if I don't think that have these benefits, I can prove him wrong, and he dared me to find some problems in ExpressVPN. And so there I began, just looking at the ExpressVPN binaries, and I started with looking at the top driver. And basically, the top driver, it's what creates the virtual network kernel interface, which connects to endpoints. And so open the binary in IDA, driver entry function, we can see miniport driver characteristic file structure being initialized with a lot of callbacks. And one of the interesting callbacks is the miniport send net buffer list, which basically will forward data to the driver. And so this is the function definition. First, we have some verification, and then we will call to top adapter transmit in a while loop. Now, this is the top adapter transmit function. And first, we can see it got Attendees allocate memory with tag priority. Then it will get this data buffer allocated, and will memory move to it. Now, this is the prefix of it, right? And so, as we can see here, we have the data length plus 24 in the allocation. And we can see here in the prefix of the function that we will get this value from RDX plus 18, put it into EBP, which is a short one, and then pass it forward. And so the logic, the calculation of the size will be something like that, which if we'll pass enough, like a big integer, will have an overflow. It's an integer overflow, a classical one. And so after that, we will get this data buffer, and we'll memory move it. And so, but we can notice that it will be moved with the data length, the original data length, not the plus 24. And so what we'll get is basically we will move all the big chunk of memory onto the 70 allocated bytes. And it is a wild kernel overflow. Now, exploiting wild kernel overflow and achieving code execution, it's a hard task. It's not something I will talk about it today. But basically, there are a lot of cool research out there how to do that. And so after that, I just wrote a fast POC to crash the system, and actually forgot it for a couple of days. And a few days later, I looked at another VPN, at Proton VPN. And so again, another driver, another top driver, open and find the top adapter transmit function. And again, it's have the same issue, the same bug. And so as Erlinda saying here, we already seen this bug. It's the one that we seen in ExpressVPN. And so at this stage, I understood that probably there are more out there, right? Because if there's two, there will be more. And so wrote some Yara rule and executed retro hunt search in VirusTotal, and found around 50 matches. Those are part of the examples. And so we can see there are a lot of drivers with the same issue. Now, at this stage, I said, OK, it got to be something very popular, something that everybody uses, and just asked ChatGPT. And obviously, the answer was, did look at OpenVPN. It's probably it. And so let's talk a little bit about OpenVPN. Now, OpenVPN, it's very popular open source code for VPN programs. And if you search it on Google, you'll find the first probably result will be the Git repo, which has a lot of different repositories for a lot of different things OpenVPN have. And basically, OpenVPN have two meanings today, basically. The OpenVPN binary part, all the thing that does the VPNing, and the protocol which used for creating tunneling. Now, back to the things that we found. I went to look at top Windows 6, which is a Git repo for top driver of OpenVPN, and found the top adapter transmit function, and found the same Attendees allocate memory with tag priority. And this is the issue, the top packet size macro, which adds things, and this is why we have the overflow and wild kernel overflow. And this is like the first base for all these issues is on OpenVPN top Windows 6. Now, OpenVPN, as I said, has a lot more things to offer. And basically, this repo is actually the repo that runs, it executes the tunneling and the VPNing, let's say. And it's very popular, as we can see here. We have another repo, which is the OpenVPN GUI, which is actually the GUI version of managing OpenVPN on Windows. And we have the top Windows 6, as we talked about it. Now, OpenVPN, basically, the server client architecture of that will be, we have the OpenVPN client that will connect to the server over a cloud or a network and create a tunnel with the keys and everything, how it should behave. And then we'll pass some data through the tunnel to the OpenVPN server and back again. And the relevant part is that on endpoints, OpenVPN have two parts, the user mode and the kernel mode, where the kernel mode basically is the part that manages the tunnels, and the user mode have all the configuration and all the logic for the VPNing, let's say, definitions. Now, as I said, OpenVPN is also a protocol. And so basically, a standard packet of OpenVPN will have the next structure, it will have the packet length, and then it will have like the payload, the opcode, the key ID. For instance, if we want to soft reset the tunnel or maybe hard reset it, maybe start switching keys, stuff like that, we'll have here the ID to identify that, and then the actual payload. And so obviously they're like a pickup parser, like a Wireshark parser for that. And there are a lot of documentation about this protocol on Wireshark, on the OpenVPN page, on Wikipedia, and a lot more places. Now, OpenVPN, because it's widely used by basically almost all industries, it has like compatibility for all the main operating systems today, such as Mac, iOS, Android, Windows, Linux, and whatnot. And so they achieved that by a number of basically techniques. They use, for instance, something that called data control offload, which will basically allow to read and write faster to the kernel memory for information to pass through the tunnel. And they have those for different operating systems. And basically, the difference between the data control offload and the top Windows 6 is that on Windows, the top Windows 6 is based on Attendees, and the data control offload is doing it faster and it's actually newer. Besides that, they have a lot of macros to define different logic if you're running specific operating system. Elifs includes, different includes, and whatnot. Another very interesting mechanism of OpenVPN is the plugins mechanism, which allows authentication against LDAP and radius backends and servers. And how we achieve that? Basically, we can compile an SO object, shared object, or an NTLM with exported functions, and then the OpenVPN binary will load it and execute it. Now, those are the functions that we need. Open will be the initialization of this plugin. Function is the function that will be called every time we want to execute specific logic of the plugin, and then close and onboard are self-explanatory. For instance, here we have an example for the plugin code. We have the open function here that will define the username, the password of the context. And then in the function, we can see authentication with those fields stored in the context. And well, the underline here is that plugins are pretty cool and allow a lot more functionality to OpenVPN. Now let's talk a little bit about the security side of OpenVPN. And basically, OpenVPN on Windows have OpenVPN Server Exe, which is the anti-system service. And it has a name pipe by the name OpenVPN service, to which, when connected, OpenVPNX will be spawned for specific client. And so how it all works, first, the system, system service, when it starts to run, will create the name pipe, and then create a thread to handle queries on that name pipe. And so there are specifically defined users who can do that, and specifically defined location that they can do that from. And after that, if a client will connect, it will get the startup data from the client. Startup data will look something like that. It will contain the directory in which the configuration for OpenVPN is residing, and a path to log for that as well. And after that, after the startup data arrives to the NT system service, the NT system service will impersonate the client that connected to it. Then it will do all validation for user SIDs and stuff like that, checking that the user is actually authorized to connect. After it, another name pipe will be created, a new name pipe. Let's call it an inner name pipe. And so the handle will be passed to the newly spawned process for the inner named pipe, right? After that, the actual process of OpenVPN will be created for actually executing the VPNing logic. Now, after that, we'll have something like that. We'll have the OpenVPN service exe system service, which have two named pipes. First is the OpenVPN service, the outer named pipe, and then we have the OpenVPNX, which is the spawn process, and it has the inner named pipe, for instance, here by the name service 1234. Now, and why we need this inner pipe? Because the OpenVPN process that runs, it runs in lower integrity levels, and so if it wants to do some elevated logic, for instance, adding IPs, removing IPs, changing DNS configurations, you need to request it from the system service. How will it do that? It will do it by sending specific message through the system service of OpenVPN, and then the OpenVPN system service, as shown here, will handle those messages accordingly. Now, there are a lot of types of messages, for instance, messages to address, add, or removal, route, the same, and DNS configuration, and even an ACK message. And so, for instance, if the OpenVPN decided to add some route, it will send a route message to the system service. The system service will handle this query and then return back an ACK indicating if it was successful or not. For full picture, this is how it will look on Windows system. We'll have the two already known processes, and then we have the OpenVPN GUI, which will actually create the first communication to the system service to the external outer OpenVPN service name pipe. And now, if we want to look at this at like network side, we'll have it something like that. We have the channel through which the data will pass to the OpenVPN exe. We have the inner and the outer name pipes. And another interesting thing here is that we got the plugin that is privy to the data going through the channel. This is about OpenVPN. Now let's talk a little bit about potatoes. Everybody loves them, specifically dudes from Lord of the Rings, and me as well. And we'll talk about Windows privilege escalation techniques, which called potatoes. There are a few of those, hot, hot, and lonely. And the idea is there that through some trickery and some tricks on the operating system of Windows, privilege escalation will be achieved. For instance, a hot potato is basically a scenario in which an attacker will wait for endpoint to try to update. It will then send the malicious WPD that file, which will trigger an NTLM authentication with the attacker, and then it will relay the NTLM attack to the SMB server and achieve anti-system authority, and which is the P here. And now let's get back to OpenVPN. So the second issue I found in OpenVPN was here. This is the while loop that reads amount of bytes to read from the name pipe, from the inner named pipe from the OpenVPN exe, and then calls the method call handle messages. Now, this message defines a struct of message of different types, and then basically reads the amount of passed bytes into that message. And so obviously it's a Stack Overflow, because if, for instance, here I have an example of message, which all of them have the message header, and then the fields of a specific message, as for example, address message T will have family, address, prefix, len, and iface. And so if I'll send another message example, if I'll send enough data, they will overflow all these fields and go out of the message. And this is a Stack Overflow. And obviously, after a first exploit, we'll have something like that. Fast fail stack cookie, check failure, which means we have a canary, stack canary here. And so let's read a little bit about this canary, understand what we can do with that. This is the prefix of the method. Here we can see we're storing the security cookie into reps, and then storing it with RSP, and then storing on this RSP again. And the security cookie defined as follows, but obviously somebody will render it when the program starts running. And in the end of this function, in the suffix of this function, we can see a call to security check cookie, which will retrieve the cookie from the stack and then calculate the value and check if it's OK. If it's OK, it won't call report failure. But if it is not a good value, report failure will be called, and where fault will execute, as we know. And so let's find where this cookie defined. Obviously, security init cookie. Now, the basic idea here is that we'll regenerate the value of the cookie based on a lot of information that we are not, as an attacker, we are not really privy to. And so the idea here is that to successfully exploit this function, this vulnerability into code execution, we'll need to have a read primitive on the memory, on the stack memory to retrieve it. Now, I haven't found this one, and so basically what it leaves us is with stack code that will crash the service or crashing the service with stack code, and where fault will be executed. And so now let's talk a little bit about problems in name pipes. And basically, there are two very popular ones. First is called the creation race condition, which basically means if I have a server which creates a name pipe, and then a client will connect to this name pipe, if somebody creates this name pipe before the server, the client will connect to the first instance of this name pipe, basically to the malicious app. The second issue is the superfluous pipe connectivity issue. Basically, it states that if a client connects to a name pipe, it doesn't really know who is the other side of the name pipe. And so if it's a bad actor, it will have an issue. And now let's connect all those dots into having an LPE, which I call the open potato, because it's basically based on potatoes family of vulnerabilities, and it's OpenVPN related, and obviously open potato is a good name for that. And so we will begin by actually crafting malicious DLL, the malicious plugin. We'll make the OpenVPNX load it, and then through the plugin, we will send a malicious message to the anti-system service, which will crash it. And then it will open a window of time for us, in which in this time we can reclaim the OpenVPN system service name pipe. And then everybody that will connect to this named pipe unknowingly will connect to us. And then we can basically wait for a strong connection for a privileged user, and then we can basically impersonate him and have an LP. And so this is the main of the DLL to do that. And then we have parsing of the command line argument that passes the handle. Then we will duplicate this handle and basically send the packet. In this case, the message that will kill is just enough Zs, and it will kill the system service. After that, we will reclaim the OpenVPN service name pipe, and then basically we will execute the same flow that OpenVPN executes, right? We'll wait for connection. If a connection occurs, we'll start a new thread to handle it, and then we'll get the start with data and then impersonate the named pipe client. And then we'll check if the client that we already right now impersonating is a strong one. And if it's a strong one, we can execute a binary that we want for further exploitation. And now this is the demo for that. Right side, we can see the user with the SE assigned privilege and SE Brownell token privilege. And then we'll execute the exploited. We'll wait for the crash of the system service. And then on the right side, we will connect to it with a stronger user. For instance, here in the example is the anti-system. And then a stronger client will be spawned, anti-system elevated, with all the privileges that anti-system has. And we can see here it's actually anti-system, which is yeah, pretty cool. Nice. Thanks. Now, okay, so the next stage obviously would be how can we do it remotely? And well, obviously we can use name pipes remotely, just we need to be able to use shared resources. And so those are files, folders, and printers. Now, basically on Windows, they're usually shared with SMB or SMB2 or their variants. And also, for instance, if you want to be able to access server 01 for share folder for file example, we'll basically need to use something like netuse to be able to access this server. And so if we do that, we'll obviously need the credentials for that, but then we'll see the APC folder, which basically contains all the inter-process communication things, such as named pipes. And so we can access remote named pipes, but we need credentials for that. And for instance, if we look on a pickup file with this behavior, we'll see actually the request for the APC and the specific SMB query for that. Now, basically, there are some security mechanisms on Windows that probably won't allow you, for instance, if you're an anonymous user, to connect to existing named pipes. They have specific definition for those. But those aren't preventing me as defined user with credentials to connect to them. And so as long as I have credentials, I can do that. And so let's talk a little bit about how can I get credentials. Now, basically, all modern APTs have tons of credential hijacking, stealing techniques, and every time another pseudo-new technique created. But the idea is remain that everybody want to somehow get credentials and use them further. For instance, the Russians with the goose egg, or the infamous Mimikatz, and even some credential stealing from web browsers. Now, a lot of those aiming at stealing NTLM hashes, which is NTLM is the Net LAN Manager Authentication family of protocols, and basically they are there to manage securely authentication between managed endpoints. And for instance, the full flow of NTLM handshake will look something like that. We'll first have the NTLM CSP negotiation, then we have the proceed more information required with the NTLM servant challenge, and then we have the answer with that with the NTLM proof string, and then we have the full answer with a lot of fields that's stored in the NTLM v2 response. And now if we use Kali and responder, we'll basically be able to capture those if we sniffing on the network, right? For instance, here we have the username with Gandalf, and then the domain, then the NTLM server challenge, and all the extra hash payload. And obviously, we would like to crack that to get the credentials. Now, this can be achieved through tons of ways, but basically, John the Ripper and Hashcat are like the prime candidate for those. And I proceed with Hashcat because it's very good with GPUs. And basically, the first attempt was just using my Rockstrix with RTX 3070. And it has almost 6,000 CUDA cores, and basically installed Hashcat on it and executed, which on those on this hardware can basically break 2,800 million hashes per second. And basically, first attempt was like break some very easy password, very short one, and obviously it broke it momentarily. But then again, if I'll try to break 9 chars password, it will take me about 4 years or almost 5. Now, nobody got time for that. And basically, the next solution is obviously let's construct a full rack with a lot of like GPUs myself. Again, I don't really have no time and no money for that. So I'll proceed with like a modern solution. Vasta is like a platform on which you can rent machines with a lot of computing power, a lot of GPUs. And for instance, here I rented for $9 an hour a machine with 18 RTX 4090. And so here I'm installing an image with Hashcat on it. Now let's compare a little bit about the machines. The 18 RTX 4090 has basically 50 times more CUDA cores. And so the relevant question is, will it like run 50 times faster? Obviously, the answer is not, because there are software optimization, CPU memory bottlenecks, even like the speed on which it can connect all the cores, it's different. And so, like in theory, it could be 50 times faster, but it's not for sure. It's not given. And so, after installing the machine, I executed Hashcat on the given password from earlier. And basically, it took me less than 3 minutes to break it, which was pretty cool. And here, the actual password. Now, if you remember, we did it so Herlinda would be happy, and for us to be able to execute, like to connect to remote name pipe. And so here, we will use these credentials to actually net use on the remote machine. After that, we will actually connect to the name pipe. And the second stage of the exploit will be basically telling the NT system service of OpenVPN to load configurations from an attacker-managed share, as shown here. And then the configuration for that instance will have the directive to load a plugin, which is again located on the remote share of the attacker. And then basically first attempt will fail because we need to allow access to this share for anonymous users because it will do this impersonated. And so we need also allow everyone to access to the share. After we'll do that, we'll actually see the access to this share. Then we'll see the query for the configuration for OpenVPN. At that stage, the NT system server will already execute the OpenVPN exe, which will then try to load the simple DLL plugin for our remote machine. And this is the example for the RCE. We can see here on the attacker machine, this attacking script executed, which will basically connect to the remote name pipe on the remote name endpoint and will execute the OpenVPN exe on its behalf, which will then query from the share on this machine the DLL, which in this case will basically drop some files on the desktop for some visual effect. Yep, this is it. Now let's talk a little bit about how we can chain all of this together. And so obviously the porting of the LPE onto the RCE will be pretty easy because all I need to do is like port all the LPE logic into the plugin, and I can achieve that by basically adding resources to the plugin and then drop them and execute them. Now another thing that we need to take account of is that OpenVPN executes in low integrity level, and so we'll have to execute log on user with the stolen credentials to allow us to actually execute the impersonation of a stronger user. And now, let's say we achieve that, what next, right? And so APTs usually using a lot of techniques to attack the endpoint, and then they want to make the grip of the endpoint stronger. Usually via techniques such as bring your vulnerable driver. In this case, we can easily write a script or a code to the plugin and port it into the plugin that will load signed but vulnerable third-party driver and execute it vulnerabilities to achieve read-write primitives into kernel, for instance, right? Or maybe, we can do it based on the dbutil to free system driver, or maybe the Foxborough driver is shown here. Another technique would be the living of the land, which again will basically use installed application to achieve the same effect. And third one, the one I love the most, is the exploiting vulnerable driver that comes with Windows installations, such as Lazarus project did this year. They actually exploited a cool vulnerability in AppIDSys, which allowed them to change the previous bit of the state, and then that allowed them to have read-write primitives into the kernel. And so usually after that, attacker will try to evade or basically kill protection mechanisms, such as antiviruses, defenders, and stuff like that. But we all know that those are protected by PPLs. Now, PPLs are protected process light. They came to existence around 2008. Basically, they were created to protect for DRM. The idea was, let's protect, like, for instance, Blu-ray movie. We want to be able to play it on one hand, but we want we don't want other process to be able to like copy its things from the process. And so PPLs are the newer version of the protected process, and basically the difference is that they all have signature and in the actual binary part of the binary, and they when they are loaded, they are validated, and then after they're executed, no usual process can touch them. But the difference is that PPLs have a number of different signers, and they have an hierarchy. And as higher the signer is, it is stronger, which means it can handle with all the signers lower than that. But for instance, PS-protected authentic code light can't like write or read, I'll say, light memory. Now, if we want to find the definition and the values of the actual structure that hold this on Windows, we can use WinDBG. We can then basically check the PS protection struct and find it has type audit and signer values. And then we can find the definition of those enums to find the values actually mean. And for instance, if we look at LSAS, we can find the eProcess struct, and then with some offset from that, we'll have the field of the PS protect. And then we can find that in this example, LSAS is PS protected, type protected, which makes sense. And it's signed by PS protected signer with Win system. Now, for instance, if we would like to unPPL a process, for instance, here, if we want to unPPL Win init, for instance, if we want to kill it, on the regular execution of a Process Explorer, we won't be able to do that because Process Explorer isn't a PPL, right? But what we can do, we can attach kernel debugger with Windows and actually change the, find the PS protect field of LSAS, of Win init exe, and find its value, write it with these zeros, and then we can actually kill it, which is cool. Now, this actually what exactly I have in the next demo. I'll have a full chain. The chain will start with the RCE that we already seen. Then we'll execute the LPE part, the stage 2, that will wait for a stronger user to connect. After that, after a stronger user connected, we will execute stage 3. In this case, stage 3 will actually exploit the same vulnerability in app-IDSys, which will land us with Windows read and write primitives. And then with those, we will actually find the PPL process that we want to kill. We will find its PS protect field, override it with zeros, and actually kill it. So let's watch out the full demo. First, here is the part on the attacker. We'll execute the remote code, the RCE, waiting for it to connect. And then it will take a second. We can see the stage number 1 log being dumped on the attacker share, and the stage number 2, which means the part that's waiting for the strong connection is already there. And then we'll have here administrator connecting to the OpenVPN. And we can see here that it fails to connect because the anti-system service is not up, and so it fails to do that. But then we kill the PPL, and then we'll have the classical we kill the critical process issue. And so mitigation from those are available on a lot of Windows and Microsoft products such as MD, MDVM, Sentinel, XDR, and Defender for IoT. Sorry about that, I have to take. Yeah. Now, something very cool I want to talk about is that OpenVPN were very cool and very nice on the whole process of those vulnerabilities. And the idea is that somewhere on December 20, give or take, I found all those vulnerabilities, submitting them on February 14th. And then a little bit more than a month, they released an actual patch to patch all of those. Now, it's pretty crazy because if you think about OpenVPN, it's very popular and used on a lot of locations, millions of devices, and release a full version with patches for vulnerabilities. It's hard, and come to think about it, it's an actual open source, and then a lot of community folks should go over the patches and see if they can see it. And all of that was done in a month. And it was pretty crazy and pretty fast. And very thankful for that. And they did it very fast. Now, the key takeaways here today are, first, use long passwords, but not complicated passwords, as this KCD shows, just a long password that it's easy to remember. And another cool thing about it is that sometimes very complicated issues need or have very easy solution. In this case, OpenVPN just allowed only execution one directory for the configuration of OpenVPN per user. And so the LP vector and the remote code execution vector aren't available from here. And the third one is that all of the things that I showed here today are old concepts. Nothing's new here, nothing new under the sun, and yet I still was able to get a full-blown chain here. And so those things shouldn't be overlooked. And we finished, and we have some time for Q&A.